In this infinite power tower of an infinite series, we want to see whether it converges, and if it does, then can we solve this infinite power tower of infinite series quickly? So there is a quick way to answer this question. Focus on the base of this infinite power tower, which means 1 plus 3, and divide by 5 plus 7. This is obviously 4 divided by 12, which is 1 over 3. So base is 1 over 3. Now, let's look at the first exponent. It is 1 plus 3 plus 5 in numerator, the extension of the previous numerator, and then 7 plus 9 plus 11 in denominator. So if you add them up, you end up with 9 for numerator, and then 7 plus 9 plus 11 is 27. So another 1 over 3. Interesting. If you look at the second exponent in the power tower, you can see that it's further extended version. So numerator is 1 plus 3 plus 5 plus 7, and denominator 9 plus 11 plus 13 plus 15, which if you add them up, then you can see that numerator becomes 16, denominator becomes 48, which is another 1 over 3. So interesting. Looks like the base and all the, at least the first, second exponent, they all are 1 over 3. So as if we are dealing with a problem that looks like it is in the form of 1 over 3 to the power 1 over 3 to the power 1 over 3 and goes forever. So effectively we are dealing with a tetration or infinitely repeated exponentiation, which sometimes people use this notation. So either using left exponent infinity, which means repeat this infinite times, or they also write it this way, 1 over 3 tetrated to infinity, and finally 1 over 3 hyper 4 to infinity. So all of these are just notation or denoting this. Okay, so if this is true, we are dealing with this problem and we need to solve this. But before we get to that point, we need to show this observation of 1 over 3 is going to be valid for the next exponent as well, because this is going to be an infinite series effectively in numerator and denominator. One quick observation and quick way to prove this in a neat sort of visualization would be focusing on this visualization of the numerator and denominator series. So I'm going to show you. This series goes back to the Galileo time, so it's a well-known series. So for instance, focus on the first exponent, this one. So let me just highlight it again so that this one. So the first exponent, 1 plus 3 plus 5. So we are talking about 1 plus 3 plus 5. So effectively, as we added up, 9 dots here. 9 circles. So I'm going to put them in this triangle. That's the sum of the numerator here. Okay. One other thing I'm going to do is, if you focus on denominator, you have 7 plus 9 plus 11. So you're talking about now adding up these guys. So 7, 9, and 11. So those are all the dots, all the circles. We need to add them together number-wise to get to the sum of the denominator, which is 27. If you take a look at this beautiful visualization of it, you can see that we can sort of show them like this. There you go. And I can, just for the sake of better visualization, I'm going to use a different color. So there you go. And finally, this one. So clearly, these 3 rows are the sum of 7 plus 9 plus 11 in terms of number of circles, and these 3 rows are the sum of it's the sum of the 1 plus 3 plus 5. So we can see that the 7 plus 9 plus 11 effectively is 3 times or 3 repetition of the same triangle that we have here. So that shows that with this progress that we have, if you even go further, so this is showing, sort of visualizing why we are getting 1 over 3 for this interesting formation. If you continue and proceed with, say, the next exponent here, if you proceed with the next exponent here, now using the same illustration, I can now expand these triangles. So let me do so. And you can see now I can expand it to this situation. So now here is my triangle, because I need to add 1 plus 3 plus 5 plus 7. And so this becomes 1 plus 3 plus 5 plus 7. And I can do the same thing as I did before. You can see I have a repetition or copy in a sort of inverted fashion of that triangle here. And then I have repeated version of that triangle here as well, and here as well. So same number of circles or dots. So effectively now I have 1 plus 3 plus 7 in that triangle, and then in each of these repetition below I have 9 plus 11 plus 13 plus 15 as in the denominator of the second exponent. So there you go. This is, and it's obvious why we are observing that, because this is 9, this is 11, this is 13, and here are 15 of these circles. So again, proving that what we have in numerator is 1/3 of what we have in denominator. So this is a visualization that is highlighting why we are observing 1/3. Okay, with this visualization in mind, there are other techniques. There are purely algebraic techniques to prove that this infinite summation numerator denominator, if you keep doing so, it always get to 1/3. But here in this video, I just stay here and just rely on this visualization. So let me move this away, and I'm going to now focus on this tetration. So I'm going to focus on this infinite tetration and prove that, or investigate that this is going to converge, and what is the value of it. Okay, so in this infinite tetration, symbolically noted this way, we can say, let's say we want to find the value of this. So let's say this whole thing is equal to x. So x is equal to this infinite tetration. But then when you notice that actually it keeps showing up again, because the whole exponent of the base is another repetition of x. So I can say the whole exponent is x, and basically this whole thing is effectively, we have x is equal to 1/3 to the power x. So we need to solve this. There are many ways to solve this. One way is the visualization again. So I'm going to show you visualization that I have. So I did the plotting in MATLAB. So you can see here, first the non-zoomed version. So x-axis in this plot, let me just clean this up so that it's clear. So x-axis in this first plot that I'm showing here is, so x-axis is the x value, this x, and y-axis is showing two things. One, I am effectively showing this as y equal to x, that's one curve, and I'm showing this as y equal to 1/3 to the power x. So I have two equation or two curve, and I'm interested in finding the intersect, exactly where they are crossing. So there you go. This point is a crossing point, and I'm going to highlight the color so that it's obvious which one is what. This one is the red one, and the other one is the blue one. So okay, so the other one is the blue one. I'm going to write it here. This one is y equal to x, and this one here is y equal to 1/3 to the power x. You can see that they are monotonically increasing and decreasing. Y over x is just, y equal to x is just a line with a tangent of 1, and the red one is just a curve that is monotonically decreasing. Maximum value at x equal to 0 obviously, and is equal to 1, and as x is increasing, then the y is decreasing. You can see we are dropping. So when they are meeting at one point, that's a unique point, and if we zoom around this area, we get to the second plot that is shown here. So this second plot is when we zoom into this area, zoom in very much, so that now we can see actually the crossing point, and you can see that on the x-axis. So we have this crossing point of the two curve very close to 0.48 and away a little bit from 0.47. So it's approximately, if you take a look at it, it's approximately 0.5, I'm going to highlight it here, 0.5478, roughly, in that ballpark. So that's the answer to this question. Basically, if we prove that these two really have a intersect, or let's say overlap, so there is a unique answer for this equation, the equation that is shown here. That unique answer is x equal to 0.5478. That's the answer to this equation. So basically, yes, this whole summation that is shown here, it has a unique solution that's going to be 0.5478 for this whole thing. And we solved it. There is another way to solve this as well. So aside from the fact that I just proved that this whole thing converge and there is a unique solution for it, which is this one, using just a visualization and just graphing, there is a algebraic way to do so. To achieve that, which is my second method, let me just remove this here. So I'm going to remove this plotting that was used to show we are dealing with 1/3. So if I remove that, then here is the algebraic method. So I'm going to show second method to prove that x to the power 1/3 to the power 1/3 to the power, so we got to the point that infinite tetration became this one. So to solve this, second method to solve x equal to 1/3 to the power x. So let's say we want to solve this and we don't want to use the graphical method that I showed. So of course, one way to do this is thinking of this as, let's say, if we can linearize this to a reasonable extent. So imagine we have 1/3 to the power x as a function. I can use Taylor series expansion, so Taylor series, and knowing that 1/3 to the power 0.5, which becomes 1/rad3, which is roughly 0. So I think 1/rad3 is close to, just double checking that I'm not making a mistake here. So let me just do a quick calculation. So 3 and then rad2 and then inverse 0.5774. So 5774 is not that far away from the target. So I'm going to set in the Taylor series expansion. So Taylor series expansion says if you are trying to approximate f of x using a base point, you can say f of x is equal to f of x0. So you're trying to approximate starting from a base point, reference point, and then we can say x minus x0 divided by 1 factorial, and then we have let's say the first derivative of f when we set x equal to x0, or basically writing it in an easier way, we are saying f prime of at x equal to x0 as a first order approximation. It makes sense because then as we are doing, next term that I'm neglecting is the term that says in the Taylor series expansion x minus x0 to the power 2. But then if I use my reference point as 0.5, so I'm going to use x naught or x0 as 0.5, as my approximation point, you can see that the target is very close to it, and therefore x minus x0 is going to be a small number. Raising to the power 2, I can neglect it. So that's why for the next term in the Taylor series expansion of this approximation, I am neglecting the second derivative of f at x naught or x0 divided by 2 factorial. So I am effectively neglecting this, saying it is approximately 0. So I am sticking with approximating 1 over 3 to the power x. So my function is 1 over 3 to the power x, and I'm trying to approximate this function at x close to x0 or x0 0.5. And I am going to only use these two terms from the Taylor series expansion of f of x. So basically, I am just saying, using Taylor series, keep the left side. For the right side, I am going to say use f of x0, but x0 is at 0.5, and use x minus 0.5. So here I am keeping x, but I'm setting x0 to 0.5. So, and then divide by 1 factorial, which is 1, so no division, and then f prime at x0 equal to 0.5. So the only thing I need to do is I need to just compute f prime, and that's it. All right, so my equation therefore becomes x is equal to, well, f of 0.5 is simply 1 over 3 to the power 0.5, which I just showed you. So this one is f of 0.5, which is, we just found it, it's 1 over rad 3. Keep it. And the next term is x minus 0.5 and f prime. It's not difficult to compute f prime for a function like this. It is as simple as, if you do the quick calculation, it is as simple as just ln, so natural logarithm, at 1 over 3, and then times 1 over 3 to the power x. So maybe I just clearly write it so that there is no confusion. 1 over 3 to the power x, which is x naught, because we are doing 0.5 to the power 0.5, which effectively becomes 1 over rad 3. Okay, so the nice thing is I can just multiply both sides of this equation by rad 3, and what I get is rad 3x is equal to 1 plus x minus, so 1 plus x minus 0.5 ln 1 over 3. Okay, so the last step here I need to do is just moving x and just shuffling things around in this equation and then solve for x. So now you see that the reason that I did the Taylor series expansion, because otherwise, because solving this exponential equation is not straightforward without the graphing. But then if I do the Taylor series expansion like this, then it enables me to quickly solve it. So now I can just say, based on this, you can solve, and x becomes equal to, so if I shift things around, then, and instead of ln 1 over 3, I can say minus ln 3, and then therefore the answer for this question becomes 1 plus ln rad 3. So let me just clearly write it. Divide by rad 3, and then we have, making sure I'm not making a mistake here, ln 3. So that is the answer, or rough approximation of the answer for this equation. And if you calculate this, interestingly, the answer becomes roughly equal to 0. So this is roughly equal to 0.5473, which is very close to what we found earlier. See, this is what we found algebraically using Taylor series approximation, but that is very close to what we found using just plotting, which indicated the answer is 0.478. Here, 0.5478. Here we have 0.5473. So very close. So I just wanted to highlight that it's not as if we are enforced to always do the plotting to find the answer, though plotting is always a suggested way, because it helps us to also double check whether the answer is unique or not by examining the properties of the curves. For example, in this case, monotonically increasing and decreasing is helpful. But I just showed you that using Taylor series approximation, we can also algebraically solve and find the solution of this tetration. Okay, so I hope that this example is helpful in terms of how to deal with an infinite power tower of an infinite series, and how to examine whether it converges, and if it does, then what is the answer, which in this case is this one. Thanks for watching.